Hello everyone, my name is Scott Jones, Vice President of Atlantic. Today I would like to share some of Atlantic's technological advancements and how you, the client, can benefit. As improvements in linear mode LiDAR progress, the captured detail improves and opens the doors up to new and exciting ways to extract and verify data. These opportunities are all thanks to our purchase of the G2 sled created by Optech. This gives us the unique ability to pair multiple T2000 linear mode sensors together to increase our points per meter capture rate. With more points per meter comes greater detail in desirable target collection. Now, to unpack a little bit about this, in previous videos I discussed the installation and the concept of the G2 sled and the coupling of the two T2000 linear mode sensors. As a representation of that, let's zoom in to some data and visualize it. In typical data sets, we're able to see kind of a linear line placement. The lines stack close together and invariably leave holes or erratic spacing between scan lines. As we move through the G2 set, you can see that the patterns closer and closer together and become more uniform with any given area. This is what we call the flower pattern. See almost a circular placement of points, allowing for even distribution or greater distribution within a given cell. This allows us to delineate, identify, and better understand what the sensor is seeing. Now let's look at this particular data set. This was flown, I believe, 60 points per meter. And again, with our T2000 sensors together in the G2 sled, each sensor is a 2 megahertz system, or 2 million points per second. When we pair those two together, we are looking at 4 million points per second. So very easily, we're able to achieve that 80 to 100 points per meter collection rate. This allows us to get greater detail than we ever have in the past, and allow us to do fantastic things. So let's look at this sample of field collected VRS data collected by our survey crews and see how it compares with our algorithmically calibrated test data set. So with this cross-section view, we are looking at point cloud data colored in various colors of green and blue and yellow, and we have our control points with the red circle and red crosshair. As the descriptions are stated above, we have a center line, pan, toe, let's zoom in here, top and top back curb, and then a ground point offside. Let's thin down the cross section so we're not looking at so much data. I'm going to break this down first at a 2 meter swath. So what that means is that we are zooming in and looking at a cross-section view with a 2 meter swath allowance. So this allows us to look at every point in the cross-section within this 2 meter swath. Let's start with this. Alright, so as we zoom in, let's start with the toe. So at any given point we're doing survey collection, top and toe is always a must-have in engineering projects. Within this view, we are going to do an approximate vertical comparison between the checkpoint and the closest LiDAR point cloud point within that cell. So let's give us some best case scenario. We're looking at possibly 8 millimeters. And let's give us some worst case scenario. So let's go all the way down here. So at worst case scenario, we're looking at 0.25 centimeters from the closest LiDAR point cloud point to the toe point collected from our survey crew. Not too bad. Let's do one better. Let's look at the top point. Alright, so again, we are going to do a best case and a worst case scenario. Let's measure vertically the top survey checkpoint down to the closest LiDAR point cloud point. 1 1 centimeter. Let's do worst case. Let's make it a little bit better. Let's go down to this one down here below it. We're looking at a 2 centimeter vertical difference between the checkpoint collected from the survey and the closest lidar point cloud point. Right. So let's say we're looking at points closest to the checkpoints collected by the survey. Let's do this again. So again, this worst case scenario, we're looking at 2 centimeters vertical difference between the top of curve and the closest lidar point. Let's look at the toe again. Even still, so even from here, if we were to measure and approximate to the top back, we're looking at 1.5 centimeters. So as you can see, with greater detail becomes greater accessibility and analysis of targets. And as we increase the point density, our ability to see what's actually there within the lidar becomes greater. Now, this is unclassed, algorithmically calibrated, as in no human interaction has been touched with the points, therefore no analysis from our technicians have been done. This is straight out the box, straight out the processing, and right off the bat we're sitting at 1 to 2 centimeters vertical difference between algorithmically calibrated lidar and VRS checkpoint data. Hopefully this was helpful in discerning how well lidar projects can fit to field collected survey, and I hope that we can prove that this solution is a great option for any client, for any project.